Welcome to the 7th lecture in Riparian Function and Management. In our last session, we examined riparian recovery of Bear Creek and the dynamics and processes associated that recovery story. Bear Creek is one of the most noted recovery stories ever recorded. It is currently a perennial flow blue ribbon trout stream from no fish. The wet riparian area, sponge area, was measured at 12 acres per mile, up from 4. The water storage capacity was calculated at 6.4 acre-feet per mile, up from just 1.5. And only 100 feet of active bank erosion was measured within the reach, down from 12,500 feet. In this lesson, we will evaluate Lane's balance, a physical relationship between water and sediment in the stream channel. If you will recall, our definition of functioning condition involves having enough stuff, vegetation, landform, or large woody material to first and foremost dissipate stream energy. So it is physical function that produces the values that we appreciate and demand from our creeks and rivers. Note the key terms in this description are banks, erosion, sediment, and flow. Emory Lane was a hydrologist with the Bureau of Reclamation. He presented a milestone paper entitled The Importance of Fluvial Morphology and Hydraulic Engineering to the American Society of Civil Engineers, July of 1955, which focused attention on a relationship between water and sediment. The information presented in the paper led to what was first called the Lane's principle, or Lane's relationship, and became the equation-driven Lane's balance. His relationship was the first to describe the 4 basic variables of stream channel equilibrium: discharge of water, sediment load, slope of channel, and size of sediment. The natural function of rivers is to carry the sediment and dissolved solids to the ocean. Humans interfere with this function as they utilize the water resources of the earth, often without realizing that the water is already committed by nature as a carrier of sediments to their ultimate destination. In that quote, we're not sure if Lane said this, but the statement definitely describes what he was coming to realizing. This picture contained above, or seen here on the screen, let me rephrase that. This picture contained in his shows 1955 Lane standing next to a down-cut bank on the Pecos River below the Fort Sumner Dam. He coined the concept behind hungry water, which in this photo, starved of its sediment by the dam, has eaten a man-sized hole in the riverbed downstream. Lane's equation says there is a balance between the product of a river's sediment load and sediment size and the product of the river's slope and discharge. In the equation, you have QS, which is the sediment load, and in D50 is mean sediment size. QW is stream flow at bank full, and SO is channel slope, which you can remember is affected by sinuosity. So if one of these 4 variables is altered, then the channel will reach to create a new equilibrium downstream, which takes into account that change and rebalances the equation. Let's say the sediment load is changed or blocked by a dam. Then downstream, without the sediment to balance the equation, the hungry sediment, shy water, will eat more and more sediments from the bank and the beds until a new equilibrium is established. In later derivations of Lane's equation, sediment size is replaced with a relative roughness function to accommodate for friction, etc. As well, other morphologists have refined the sediment load and particle size to further modify and refine Lane's concepts. If you love equations, you can find much more about use and refinement of Lane's relationship in fluvial geomorphology texts. Sadly, over 50 years, even the basis of Lane's concept that streams carry water and sediment, and that when one variable is interrupted, others will compensate, is still mostly missing from practical resource management consideration. By putting Lane's equation on a balance beam, we can begin to visualize how channels react to change and how they regain balance. Another way to think about balance is in terms of energy. The sediment side of the balance is as the energy dissipator, and the water side is the energy generator. Land management practices and changes in land use can increase the volume of runoff that ends up in the stream channel. One initial result of more bankful stream flow can be channel degradation. Degradation can be seen as excessive erosion, downcutting, and or widening of the stream channel. All signs of too much stream energy and not enough energy dissipation. Notice how the scale becomes unbalanced. The water side or energy side becomes more powerful and the sediment side is diminished. In this real-life example on a tributary to the North Sulphur River, we can see that changes reacting in accord with Lane's balance to successive waves of development. Let me restart this. In the real-life example on a tributary to the North Sulphur River, we can see the channel reacting in accord to Lane's balance to successive waves of development, including addition of increasing amounts of impervious cover and resulting increases in runoff within the watershed. The channel starts out sitting appropriately on the landscape, sized to carry the water and sediment delivered. Then, more water without more sediment begins to be received as an area of northeast Texas begins rapid urbanization. Eroded stream bed and bank materials adds more sediment to a stream. As a means of rebalancing itself over time, a channel might adjust its slope and become flatter by incorporating the newly mined sediment. This happens through the creation of meander bends. Meander bends increase sinuosity and add to overall length, eventually reducing or flattening the stream channel slope. After degradation, notice how this scale becomes rebalanced. Though the channel remains full, it rebalances itself by flattening out its slope. In this real-life example, the channel of Chambers Creek in the Trinity River Basin, downcut and then rebalanced by flattening its channel with sinuosity. Land disturbances and human interferences like gravel mining, road building, and other construction projects can release more sediment to a channel than it has the water or energy to manage. When the sediment side of the balance experiences an increase without a corresponding increase in water energy to move sediment through the system, the stream can experience aggradation, visible as the buildup or deposition of sediment within a channel. Mid-channel deposits of gravel or sand can be signs of aggradation. Notice how the scale becomes unbalanced. In this scenario, the Q variable has been increased and the channel is being asked to transport more sediment, outweighing the energy or bankful discharge of water, QW, and resulting in a buildup of sediment in the channel. In this real-life example, suffering from years of bank disturbance, the upper Nueces was choking on excessive sediments, evidenced by mid-channel deposition. and these waves of sediment drops. The bankful energy was not strong enough to move these sediments, and they are being deposited in odd places. One way a channel can rebalance itself from an increase in sediment is to increase or steepen its slope. Channels become steeper by becoming straighter, which correspondingly make them shorter in length. This steepening of a channel slope helps focus stream energy to more efficiently move the increased sediment. After aggradation, notice how this scale becomes rebalanced. As the channel remains full of excessive sediment, it rebalances itself by steepening its slope. The original lane's balance does not consider riparian vegetation or account for the roughness and energy dissipation that it provides. The upper Nueces is beginning to rebalance its sediment load, and that recovery can be mostly attributed to the recovery of stabilizing riparian vegetation. We will examine this recovery story more in the next lesson, and we will visit this site during one of our first class field trips. Let's remember that a degraded channel is more than unsightly or inconvenient to cross. There are several hydrologic consequences to channel downcutting. This can be observed across much of Texas as enhanced runoff, urbanization, impervious cover, or just plain poor land stewardship causing more energy to reach stream channels. The result is flashier, more damaging floods, and less water stored in the landscape to feed the stream during dry times. Another consequence of too much energy in the channel and degradation is the loss of floodplain access. Floodplains are for recovery. Remember, the floodplain is the place where floodwaters spread out, slow down, and benefits of organic matter, rich sediment, and water are captured and stored. If the bankful amount of water can no longer reach over the bank, then those benefits are lost and recovery is delayed until the equation is rebalanced. A new floodplain is formed at the lower elevation. The recovery of riparian function represents an overlooked opportunity for healing landscapes. Catching water and storing water in the land. Understanding lane's balance can help interpret observed changes in stream channels, and as Lane intended over 50 years ago, his balance, if widely understood, can inform decision-making to avoid unintended consequences. Today's lesson covered Lane's balance as an equation for natural recovery process. For homework in preparation for our discussion Friday, you were asked to use Lane's balance to explain your sum of the conditions and observations you have noted in your data log about your creek site.